So far we have looked at applying the principles of complex analysis to get new flows using superposition. What I am going to do in this session is to work out a simple numerical problem using the idea of superposition, and then show you how we can obtain different hydrodynamic variables such as velocity or pressure at different locations in a specific 2D potential flow problem. So, let us look at this problem, which is about a 2D steady rotational flow and this irrotational flow is formed by the superposition of say uniform flow, we have a vortex, and then we have a sink, and the vortex and this sink are placed at specific locations. So, say we have free stream uniform flow, right, which has some velocity u. The velocity is given say 8 meter per second. All right, we have a sink somewhere, say this is a sink which has a strength of say 15 meter square per second. Okay. And say we have just a little distance above the sink, at some distance, say let me label it as A, which is given as say 1.5 meters, we have a vortex which is actually a counterclockwise vortex. So, we have a counterclockwise vortex of strength gamma, which is 25 meter square per second. All right. The problem requires us to calculate the velocity and the pressure at some point A, which is at a certain distance from the sink. So, this point A is at a distance of about L, which is 2 meters horizontally, and say distance B, which is 1 meter vertically. So, the question is saying that we need to calculate first the velocity, the resultant velocity at A, all right, and the second part is calculate pressure at point A, given that the fluid is water. So, the density is 1000 kilograms per meter cube, and the pressure far upstream, which I am going to now say is P infinity, which would be pressure which is far away from the sink and the vortex, is given to be say 10 kilopascal. Okay. Given the fluid is water, which has a density of 1000 kilogram per meter cube, given the pressure far upstream is 10 kilopascal, we are supposed to calculate the pressure at point A in this problem. Okay, so I hope the question is clear now. We have 3 elementary flows. We have a uniform flow, we have a vortex, and then we have a sink, and we are supposed to calculate velocity at some point. Okay, we could choose many more points, but let us say at this, in this case we are looking at point A. So, how do we solve this? So, think about this, right. If I want to apply the principles of complex analysis that we have been developing so far, we need to first define convenient coordinate system. So, I will define my coordinate system in such a way that the sink coincides with my origin. So, maybe I will take it in this way. that our coordinates, our axes are in the following way. We have x axis here, y axis there, and the origin is here, so that the sink happens to be at the origin. Okay. You can choose it any which way. I could even put the origin at the location where the vortex is located, the answer won't change. It is just a matter of convenience, because putting the origin at the sink ensures that the distance give from of point A, which is given with reference to the sink, is easily turned into coordinates of point A about the origin. So, what I am saying is that in this case now point A is at coordinates of 2 meters. So, I will say 2 comma minus 1, right, because it is 1 meter below the origin. Similarly, the vortex has coordinates of 0 comma 1.5, which is B basically. I can say this is 0 comma B, 0 comma A, and A becomes L comma say minus B. Okay. Now, we need to work out the velocities and also the pressure. So, the first thing we should do is look at the velocity, because you know now that in irrotational flows, if I know the velocity, I can use the Bernoulli equation to calculate pressure. So, clearly the way to begin is to calculate velocity. So, we will first write the complex potential for this case, which is f of z, which would be the resultant of superposition of these 3 elementary flows. So, we can say this will be u z from uniform flow, right. This is from uniform flow. Then we have a sink in this problem. So, its potential will be minus m by 2 pi log of z, just because the sink is located at the origin. And then we have a counterclockwise vortex. So, this is important. If you recall, if you have seen the lecture so far, you would know that the potential for counterclockwise vortex is minus I gamma by 2 pi log z minus the position where the vortex is located. So, in our case the vortex is located at a point A times I, right, that is a point A along the y axis, the imaginary axis. So, its coordinate must be A I. Okay. So, this is from the vortex, this is from the sink, the contribution of the sink. Okay. So, important points, as I said here, are that there is a negative sign here, even though the vortex is in the counterclockwise direction. Okay. And the second important point is that the location is A I, not A. Okay. A would just mean that it is along the real axis, not the imaginary axis. Okay. So, we cannot use this as log z minus A, this would be wrong. Okay. Now, let us go further. Now that we have written the complex potential for this problem, we know that velocity could be derived as the derivative of the complex potential. So, that would be u minus m by 2 pi z minus I gamma by 2 pi z minus A I. That is just a simple derivative of the 3 individual expressions, right. There are various ways to go from here. What we have been doing till now is to exploit cylindrical coordinates. Let me show you how we can do this using Cartesian coordinates. The reason I would rely on Cartesian coordinates is that I have this z minus A I. So, even if I put z to be r e I theta, it would be difficult for me to simplify that part. It can be done, but it would be slightly challenging. Let us use Cartesian coordinates, so that we can write z to be x plus I y in the complex plane. So, we will get u minus m 2 pi x plus I y minus I gamma 2 pi x plus we will have y minus a times iota. All right. So, this is what the complex velocity should look like. Now, the way I am going to solve this, and the way I expect you to work out these kinds of problems is to look at what are we heading towards. We are heading towards calculating W in terms of two components u and v, and they are separated by the fact that the y component goes with an iota, and so the real part of the complex velocity will be the x component of velocity, the negative of the imaginary part will be the y component of velocity. So, I need to somehow bring this right inside this side in this form. Okay. I need to somehow take it from here to there, so that I can then separate out the real and imaginary parts. Well, I cannot do it in this form as of now, just because iota appears in the denominator. I need to bring the imaginary iota in the numerator to be able to write it as u minus iv. So, the simplest way to do this is we can multiply the numerator and denominator by complex conjugate of the complex number that appears in the denominator. So, for instance, if I multiply this by x minus iy, the first part which appears because of the source by x minus iy, I can then bring iota in the numerator, because x plus iy times x minus iy, just this product, right. This will give me x square minus iota y square, right, such as we do a square minus b square, and that we can see would be x square plus y square. So, we now have a real number in the denominator. So, that is what we are going to do with the second part as well. So, we will write this as 2 pi, we can say this as x plus I y minus a, multiply that by x minus I y minus a, and the same thing would be in the numerator, right. And then we can write this as u minus m x minus I y 2 pi, we will have x square plus y square, and here we will have iota gamma x minus I y minus a by 2 pi, then we will have x square plus y minus a square, right. This is W. Now that iota is in the numerator only, I can now separate the real and imaginary parts. Okay. So, we can separate the real and imaginary parts, so that we can get this as u minus m x by 2 pi x square plus y square, if we were just writing the real part, minus, now if you notice from this second expression here, what we see here, the real part will come when iota gets multiplied by iota, right, that will make it minus 1. So, that will give me the real part. So, I would write this as minus gamma y minus a. Okay. Note that minus and minus will make it plus 1, and then you have iota square. So, that has to be a minus sign there. So, we will have gamma y minus a by 2 pi x square plus y minus a square, that is the real part of our solution, and then we can write the imaginary part as well. The imaginary part will come from this iota here, and then this iota multiplying by the x part here. So, we will get this as plus iota m y 2 pi x square plus y square, and then we will get minus iota gamma x by 2 pi x square plus y minus a square. So, this now we can write as u minus I v and you can note that u is given by this part, and v, or I would say minus v, will be given by this part plus, or rather minus this part. Okay. So, we can say u will be capital U minus mx by 2 pi x square plus y square minus gamma y minus a 2 pi x square plus y minus a whole square, right, and we will get v to be, or rather I should say minus v, because there is a negative sign on u minus I v. So, minus v would be m y by 2 pi x square plus y square plus gamma x by 2 pi, or rather I have a correction here. So, this should be minus v and there is a minus sign here, right. So, this should be minus gamma x 2 pi x square plus y minus a square, or if you want to remove the minus sign from both sides, we could just multiply both sides by minus 1. So, this becomes minus here and this becomes plus, that gives us v. So, this is the final velocity that we were trying to derive in this superposition problem. Now, it is fairly easy, right, we know the coordinates of point A. So, all we need to do is put x and y for what the coordinates of point A are. So, we can write, now we can put x comma y to be L comma minus b, right, which is going to be L is 2, b was minus 1, and we can also put u to be 8 meter per second. We can put m, which was I think 15 meter square per second, and gamma, which was 25 meter square per second. So, if we substitute these values, we can calculate the values of u and v, and that you can work out. You can prove to yourself that u will come out to be about 8.01 meter per second and v will be about 1.26 meter per second. So, at this point the two components u comma v are 8.01, 1.26 meter per second, very importantly both pointing in the positive direction. Okay. That is just by substituting these numbers now, and also using of course a, which I believe was about I think 1.5 meters. Okay. So, that is for you to then work out. Now, that was the first part. We were to calculate the velocity at this point. Now, how about calculating pressure? Now, the question says, if I take you back to the question statement, it says that far upstream the pressure is 10 kilopascal and the density of the fluid is 1000 kg per meter cube. So, I can apply Bernoulli equation now. Okay. We can apply Bernoulli equation. So, we know that far away from the sink and the vortex, pressure is P infinity and the velocity there is u. So, we have P plus half rho u square to be constant in the flow, ignoring all potential energy contributions. So, this should also be the same as P A plus half rho u a square plus v a square, right, which is at point A. P A becomes the pressure at point A, u a v a are the components of velocity at point A. So, we can substitute, right, we can say pressure is 10 kilopascal. So, 10 to the power 3 plus half density is given as 1000 into u is 8. So, 8 square is P A plus half into 1000 into 8.01 square plus 1.26 square. And so, P A you can work out will come out to be about 9126 Pascal, or we can say this is 9.126 kPa. So, that is a pressure at point A in this problem. So, we have now computed both velocity and pressure. So, we now have U A, V A and P A at this point, okay, and that completes this problem.